Okay, so we're ready for our next lesson on digraphs, and this is going to be on the concept of Hamiltonian. So going back to undirected graphs, you'll remember that a cycle of a graph of an undirected graph G is Hamiltonian if the cycle contains every vertex of G. Now in the directed setting, we have a notion of a directed cycle, and so we kind of get an automatic notion of a Hamiltonian cycle, right? In a directed graph, we would say that a directed cycle is Hamiltonian if that cycle contains all of the vertices. So the notion of Hamiltonian is just kind of carrying over automatically. Again, is because we have a notion of directed cycle. Anyway, we just get a kind of automatic notion of Hamiltonian. Now, you'll recall that in the setting of undirected graphs, we did not have a nice characterization of when a graph is Hamiltonian. And moreover, assuming p is not equal to np, no such nice characterization exists. So we do not believe there's some kind of nice structural understanding of why a graph does or doesn't have a Hamiltonian cycle. Now, the directed version of this problem is only getting harder. Let me just sort of point out something to you that you can do in some instances to turn a problem about graphs into a problem about digraphs if you want. If I were to give you, sorry about that. If I were to give you a little graph like, say, this, one way to make a digraph out of this is to orient the edges. But another thing you could do is you could just take each of the existing edges and turn it into a directed edge this way and a directed edge that way, right? So I could take this undirected graph and turn it into a digraph by adding in all possible edges going both ways, right? So I'm sort of forming something that looks like this. And this digraph doesn't really do that. I mean, you look at it and it's just sort of a messy version of the original. But what you should appreciate is that if this directed graph was to have a Hamiltonian cycle, then the original undirected graph would have a Hamiltonian cycle as well, right? The question of whether or not whether or not the graph on the left or the graph on the right has a Hamiltonian cycle, those are just the same question. So if it was a difficult subject whether or not an ordinary graph has a Hamiltonian cycle, it's certainly going to be a difficult subject for digraphs. And as such, I mean, it is again an NP. It's an NP complete problem to decide if a graph has a Hamiltonian cycle. So we don't believe there's any good characterization of it. And in fact, what we're going to do in this lesson is just pick off some of the sort of lowest hanging fruit. We're just going to consider tournaments. So tournaments are nice digraphs. You have lots and lots of edges around. And it turns out for tournaments, these questions are kind of fairly simple. So, let me get, actually, let me just get to a new page and define a couple terms precisely that we'll need for our investigations. First off, let me define Hamiltonian. So here, D is a digraph. If I give you either a cycle of the graph or a path, I'm going to call that Hamiltonian if it contains all the vertices. So a path or cycle, let's say a path P or cycle C of D is Hamiltonian. If the vertex set of that path is the same as the vertex set of D, or the vertex set of the cycle is the same as the vertex set of D. Now, I didn't say it explicitly here. Maybe I should. But when I say path or cycle, I mean directed path. So this is a directed path or cycle. So again, I'm going to give you a digraph. The questions of interest to us for today are, is there a directed path that contains all the vertices, or is there a directed cycle containing all the vertices? Of course, if there is a directed cycle containing all the vertices, you can throw out any edge from that and you'd have a directed path containing all the vertices. So the cycle problem is harder than the path problem. Right, anyway, so that's the name of the game. Let me introduce one further bit of notation that's just going to be helpful for us in our operations. This is the notion of in neighbors or out neighbors. So if I give you a subset of vertices, X is a subset of vertices of the digraph D. I want to define n plus of X. So these are all the vertices that you can reach by starting at a vertex of X and stepping forward along one edge. But I'm not including vertices of X in this. So in fact, let me just draw the picture. So here's X. This would be n of X, and then those are the vertices you could reach by going forward one step. I will as well have n minus of X. So, and in general, X and n minus of X might be overlapping. So let me just draw another picture. So this would be n minus of X. Okay, so n plus of X, this is the set of all vertices Y in the vertex set of D, but not in X, such that there exists a vertex in X so that you have an edge of the form XY. So there exists a vertex little x in X such that little x comma y is an edge. And n minus of X, this is similar, the set of all vertices Y in V of D without X, so that now there exists a vertex X so that YX is an edge. So that's just the formalism. So these are the out neighbors and the in neighbors. So again, if I give you any set of vertices X, n plus of X is all the vertices you can reach by starting at a vertex in X and taking a step out of the set X to a new vertex along one directed edge. And minus X, it's the same, but you're just going the other way. So all the vertices that, let's say, that are not in the set X, so that you could reach X by going forward along a single directed edge. So those are out neighbors and in neighbors. And also it's a little bit convenient to use this same notation when the set X is just a singleton, but kind of omit the curly braces. So if I give you a single vertex, say X is a vertex of D, I'm going to use n plus of X to be n plus of the set. You see how bad I am at drawing curly braces here. You see why I don't want to do it any more than I have to. Okay, so out neighbors and in neighbors, we had the notion of neighbors before. This is kind of, if I asked you to define out neighbor in the setting of a digraph, you would have come up with something similar here. This is kind of the obvious. Okay, so we've got a little bit of helpful notation now, and I want to turn to the question of when a tournament has a Hamiltonian path. And turns out this is answered very nicely. I don't think I can pronounce this guy's name. I'm almost certain this is a Hungarian. Rede? I'm not sure. These are classic theorems proved long ago by people that didn't necessarily do a lot of other theorems in graph theory, and yeah, I don't know how to pronounce that name. Sorry. Anyway, the theorem is every tournament has a Hamiltonian path. Oh, every tournament has a, what am I saying? A directed path, a Hamiltonian path. Right. Every tournament has a Hamiltonian path. That's a simple statement. It's nice when just everything in the class just satisfies it. It also tends to make it easy to prove, and indeed that's the case here. So we're going to go by induction on the number of vertices. Let's say every tournament T has a Hamiltonian path. We'll go by induction on the number of vertices of T. As a base case, if there's just one, then you have a path consisting of one vertex and this Hamiltonian. So So if v of t equals 1, you use the trivial path. And that works. So for the inductive step, we are just going to choose any old vertex v. And now here's the thing. We have a tournament. That means that, this is an orientation of the complete graph. So I've singled out my vertex v. Here it is. Now, for every vertex that is not the vertex v, either there's an edge from v to that vertex, or there's an edge from that vertex to v. Right? Because we have an orientation of the complete graph. Like the underlying graph is complete. And that means that the whole rest of my vertex set splits up into n plus of v and n minus of v. Right? So all of these vertices have a directed path to v, and all of these ones have a directed edge to the vertex v, and all the vertices in n plus of v have a directed edge from v to that vertex. And now, having drawn this picture, I think maybe a good exercise would be for you to just take a moment and try to think how you would try to prove this theorem by induction using this picture. So if you want to take a moment, I'll pause here for a second. You can pause the video and have a think. Okay, well, if you figured that out, great. Or if you're just wanting to listen along and hear the answer, it's really pretty easy. Again, the nice thing that's happening here is we're operating in tournaments, and we see lots of smaller tournaments all over the place. N minus of v, the graph on those vertices, is another tournament. So by induction, this thing is going to have a Hamiltonian path. Similarly, n plus of v, the graph on those vertices, is another tournament, and so it's going to have a Hamiltonian path. And now you're all set. You take the first Hamiltonian path, every vertex upstairs has an edge from it to the vertex v. So I can take that Hamiltonian path, take the last vertex of it, follow this edge down to v. And then from v, well, there's a directed edge from v to every vertex in n plus of v. So in particular, there's one to the first vertex of that downstairs Hamiltonian path. You put all these things together, and there you go. You found a Hamiltonian path in the original graph. So, and that's the whole proof. I will write a few more words to kind of say that. So I'm going to let, let me switch my pen back. So let's let T plus, so this will be the sub-tournament on N plus. So this is going to be my original tournament, but then I'll delete all of the vertices. I'll delete V, and I'll delete, and I'll delete everything in N minus. So this is going to be the T plus, and T minus will be the original tournament, delete the vertex V, and also delete all of the out neighbors of V. Oh, whoops, wrong kind of parenthesis. So now by induction, T plus has a ham path, let's say P plus, and let me just say T minus has a Hamiltonian path P minus. And now what we can do, we can follow the Hamiltonian path P minus, then we can go from that last vertex to the vertex V, and then go from V to the first vertex of P plus, and then along P plus. So follow P plus, then to V, then follow P minus. This gives a Hamiltonian path in the original. I'm sort of omitting a little triviality here. We've defined T plus and T minus. Those tournaments, one or the other of them might possibly be empty, right? And if it's empty, I don't want to really consider it a tournament. But you see that the same argument works. If one of them is empty, then, for instance, if T plus is empty, that just means the vertex V has the property that every other vertex has an edge to it, and you can remove it from the graph, find your Hamiltonian path, and just connect it. So, I mean, really the same argument works just fine if T plus or T minus is empty. You just have a little bit less to do. Right, and so that's that. So, in fact, every tournament has a Hamiltonian path. So it's kind of a nice feature, and it's certainly a very sort of clean proof. Yeah, I mean, digraphs are very tough business in general, but at least here our tournaments are behaving pretty well. Okay, so a step trickier here is a directed a Hamiltonian cycle in a tournament. And now for a tournament, you do have, I mean, you've got a lot of edges about. You might think that you ought to have a Hamiltonian cycle every time, but you might not. It's easy to make a tournament that's not strongly connected, right? If I suppose you have a tournament and there's a partition of the vertices so that all of the edges go top to bottom here, well, then you are not going to have a Hamiltonian cycle. I mean, more generally, if your directed graph has a Hamiltonian cycle, that's going to be a directed cycle, then your digraph has to be strongly connected, because that Hamiltonian cycle, it is already strongly connected on its own, and you're just adding edges. So, so if I give you a digraph that's not strongly connected, it certainly does not have a Hamiltonian cycle. So the question really is, what happens when you are strongly connected? And that's what the next theorem gives us an answer to. So this is Camion. And the statement is that every strongly connected tournament has a Hamiltonian cycle. Based on what I just said, you could actually, you could make this an if and only if. A tournament has a Hamiltonian cycle if and only if it is strongly connected. So as we saw, if you're not strongly connected, you do not have a Hamiltonian cycle. The interesting challenge here is to prove what happens if you do. And we are now not going to prove this inductively like we did with the previous one. There's a little bit of a trick. So, I mean, in the previous theorem, we were working with tournaments and there were no added assumptions. And that's really convenient, right? Because there are lots of other tournaments around, right? You delete any vertex or any subset of vertices, you're staring at another tournament. Here, one might go by induction. I mean, you can conceivably go by induction. It's certainly possible. But it would be a more delicate argument because you'd have to preserve strong connectivity in your tournament if you want to get something coming out. So, so that's not what we're going to do. Instead, we're just going to choose a cycle with a maximum number of vertices. So let's choose a directed cycle C, so that the vertex set of C has maximum size. And, well, now, if the vertex set of C is actually everything, then you're done. Sorry. So if the vertex set of, what am I doing? If the vertex set of C is in fact everything, then we're done. So let's suppose for a contradiction that's not true. Okay, and I think I'm going to lean here a little bit on pictures. This proof is really very complete in the notes, so if I miss a few words here, I don't think it'll be a disaster. So here's my directed cycle C. That's the best one I could find, the longest directed cycle I could find in the graph. We are going to try to, we're assuming now that this is not all the vertices, and we're going to try to get a contradiction. Now, first off, I claim that if you have any vertex that's not on the cycle, then either the whole cycle, all the vertices of the cycle, are out neighbors, or they're all in neighbors of that vertex. So in other words, I'm claiming that you can't have a vertex here that has an edge down to the cycle and an edge up from the cycle. I'm just claiming that can't possibly happen. It's actually easy to see why that's the case. So suppose, well, first let me make a quick observation. Suppose you saw this. Suppose as you go clockwise around the vertex, around the cycle, suppose as you go kind of clockwise around my picture here, you saw this. You saw a vertex V, and there are two consecutive vertices of the cycle in the directed order. Say, this will be xi, and this is xi plus 1. And suppose that xi has an edge directed from it to V, and there's an edge from V to xi plus 1. Well, then you can see how to make this cycle longer, right? This is not a particularly great cycle. You could easily have gotten one that is just one vertex longer by doing this, right? So if you had two consecutive vertices, xi and xi plus 1, where xi has an edge from it to V and xi plus 1 an edge from V to it, then you could improve. But in fact, that's what's always going to happen if you've got edges from V both ways, right? Suppose I tell you, so there's an edge from xi to V. Let's just start there. And you know that, in fact, let me not worry about the name of this right now. Suppose there's an edge from this vertex on my cycle to V. Now, if the next edge, if I move, as I move along this directed cycle, if I move to the next vertex, if there's an edge of my digraph from V to that guy, then I win, right? Then I get a longer directed cycle. If not, well, that one goes up to V just like the last one, so keep going, right? So let's look at the next vertex on my directed cycle. So again, if you have an edge from V to this vertex, then you've got a longer directed cycle contradiction. So you better not. So that means this edge has to be directed like this, but you can see I can just keep this argument going. So the short of this is if there's a vertex not on the cycle, if V is a vertex of T that's not in the cycle, then V must have the property that either everything in the cycle is an out neighbor or everything in the cycle is an in neighbor. Again, if you have this mixed case, you just start at some edge from the cycle toward V and start walking around, and you're going to get you're going to find a way to lengthen your cycle. So if V is a vertex in T that's not in the cycle, then either the vertex set of C is contained in the out neighbors of V, or the vertex set of C is contained in the in neighbors of V. So actually, we just get two kinds of vertices. So apart from the vertices on the cycle, the vertices not into the vertices not on that cycle either have the property that the cycle is a subset of their out neighbors, or the cycle is a subset of their in neighbors. And I'm gonna split these vertices. I'll give them names. So we'll define A. This is the set of all vertices in v of d without v of c, such that the vertex set of c is contained in the out neighbors. And b is going to be the same thing, except this is going to be n minus of phi. Right? So let's add to our picture here. So actually, let's see if I can drag this picture over a little bit. That's better. So here's A. Whoops. Here's the set B. And again, I know a lot about this picture. Every edge between A and this cycle is directed to the cycle. Every edge from the cycle to B is directed this way. Now, now what's going on? Well, we have to consider some possibilities. It might be that A or B is empty. Could that happen? Could it happen that there's actually no B at all? This doesn't exist. That cannot happen because in that case, this would be a directed cut. Right? That would be this would be a cut where all of the edges are directed the same way. And that would contradict the assumption that the graph is strongly connected, that our digraph is strongly connected. Remember, we have this key assumption here. Our digraph is strongly connected. So by the strong connectivity of our graph, it must be that A and B are both non-empty. Moreover, again, all of these edges from between A and the cycle are directed from A to the cycle. All the edges from the cycle to B are directed from the cycle to B. I claim that you'd better have at least one edge like this. There must exist an edge like this. If there did not exist an edge from a vertex in B to a vertex in A, then once again you'd have a directed cut, right? Because this. Maybe I should just do a different color, right? If all of the edges between the two sets A and B were directed from A to B, then this would be a directed cut, and that would be a problem. That contradicts strong connectivity. So the other thing we get by strong connectivity is that there must exist some edge that goes from a vertex in B to a vertex in A. And there exists an edge, let's say, there exists an edge B comma A such that B is in big B and little a is in big A. So there it is. So it goes from little b up to this A. And now we're going to win just focusing on those two vertices. So now let me just erase some of my picture. I mean, I realize that this is getting maybe a little hard to follow. So now, what do I know? This vertex A has the feature that all of the edges from A are directed down to the cycle. This vertex B, little b, has the feature that all the edges, I mean, it's joined to everything in the cycle. I'm just not drawing it because it's already a big mess. But all the edges between the cycle and this little vertex little b are directed toward B. All the edges, between the vertex A and the cycle are directed from A to the cycle. And now you can just easily make this longer. We're going to do exactly the same trick that we did before. I'll sort of argue it. In fact, now we just have a lot of freedom in doing whatever we want to do. We'll just follow along the cycle till wherever we want, say here. And, whoa, I didn't really mean for that to be some sort of fancy spline. We'll follow along to here, then we can go down to the vertex B. From B, we're going to follow along this edge up to A. From A, I can go down to any vertex of the cycle I want. In particular, I can go down to the next vertex that I was going to follow if I sort of kept going along the cycle instead of doing what I did. And then you just follow along. And that's the proof. I don't have room to write, and it gets awfully messy here. The picture's really where it's at anyway. Again, We've taken advantage of strong connectivity. We chose a cycle that was just maximum length. It follows very quickly that for every vertex that's not on that cycle, either all the edges between that vertex and the cycle are directed this way or that way. If you had the mixed case, you just find two consecutive vertices that allow you a little extension. That splits the remaining vertices into A and B. We proved, so by strong connectivity, A and B both had to be non-empty, and you have to have an edge from this B to A. And again, that gives you what you need for a small improvement, right? So so there's our theorem for this lesson, or our two theorems from this lesson. Again, every tournament has a Hamiltonian path, and every strongly connected tournament has a Hamiltonian cycle. And I'll stop there.